Okay, do you hear my voice clearly? I mean, people in the Zoom.
Yes, Aja, I can.
Okay, good. So I should increase this. Sorry. Oh, okay. So today we're going to talk about linear programming. For linear programming, our objective function must be linear. Okay. Also, all of the constraints must be linear. Okay. It can be, well, the constraint can be equality or inequality. It's okay. Okay. It doesn't matter. But they must be linear. All right. And more than that, the decision variable must be the real variables only, not integer. Okay. The case where integer as decision variable, in that case we call it mixed integer linear programming. Okay. It's special type linear programming because it mixed integer. Okay. When you have integer, and that type of problem, I mean, for MILP, mixed integer linear programming, you need special treatment. Okay. But what we're going to learn first is linear programming only. Okay. A general case of linear programming where we deal with real decision variable. Okay. Decision variable are real number. Okay. So this is general form. You see that we have minimized of objective function. We consider minimization of it. Okay. And because our objective function is linear, right? So the objective function can be written as C1x1 plus C2x2 plus blah, blah, blah to Cn okay? Let's say we have x1 to xn as our decision variables, okay? And where C1, C2, and to Cn are constant, right? The coefficient, we call it coefficient, okay? And for the constraint also, in a general form, we can write in this form, A11, x1 plus A12, x2 plus until, A1n, xn equal B1, okay? It can be written in this form. And let's say if we have totally m conditions, okay? Then we have B1 to be m, right? Okay. And you see that we have n variables, n decision variables, but m conditions, okay? Equality constraint. In this case, because we render every constraint to be the equality constraint, then you see that if which one should be larger, m or n? We have m condition, right? Equality constraint, m equality constraint, and n variables. Which one should be larger, m or n? Hmm? Who believe that m should be larger than n? Raise your hand. You think m should be larger? Why? What about the rest? What about others? You think n should be larger than m then? Hmm? If m equal n, what happened? Yes, it's a system of equation. Then the problem is defined, right? The solution is defined. Okay, you have solution. You have exact solution when m equal n. Then your problem is not optimization because it's system of equation, right? Okay. And if m is larger than n, what happened? Yes, it overdefined. Degree of freedom is negative, right? Negative. Okay. And if n is larger than m, your degree of freedom is positive, of course. And then that is so-called optimization problem. Okay. So you see that here because C is constant, right? C are constant. And also A are constant. Okay. And we can write this way. C transpose X. C is vector and X is vector also, right? So when you have a vector of 1 by n, right? And n by 1, you times 1 by n with n by 1. So finally you got scalar 1 by 1, right? So that is the objective function. We can write this way, right? And what about here? B is vector also. B is actually vector, right? It's m by, no, one moment, m by 1, right? So what about A? A is m by n. M by n. And this is x is n by 1. So it's totally is m by 1, right? So both sides are equal. Dimensions are agree, right? Agreement in, we have agreement in dimension. Okay. This is a standard form. This is our standard form. Okay. Standard form of linear programming. So for the standard form, the objective function is the minimization type. Okay. So if you have a linear programming, which is a maximize of something, you can convert it to minimization form, right? By multiply with -1. Okay. So all the constraints are equality type. Okay. This is a standard form. All the constraints are equality type. I will tell you later how to convert inequality to equality type. Okay. And all decision variables are non-negative, must be non-negative. If you have some variable which is unrestricted, I mean, it can be negative or positive, no problem. You can convert it to a standard type where there's a restriction on the signs, on the, yeah, must be positive only. Okay, one thing, how can we convert any linear programming to standard form linear programming? The first one, the maximization of a function, of objective function, is equivalent to the minimization of the negative of the same function, right? Okay, no need for more explanation, right? It's straightforward. And the second one, an unrestricted variable, which can, any variable that can take positive or negative or zero value, can be written as a difference of two non-negative variables. For example, if you have x1, let's say x1 here, and x1 is not restrict. Here is a restrict, right? Restrict to be positive only. However, if x1 is not restrict to be positive, you can write x1 as a maybe xa minus xb, and you restrict xa and xb to be positive. Okay, so you just change one variable, unrestricted variable, to two new variables, two new restrict variables instead. So the next one is, now we solve the first problem, right? The objective function is of the minimization type. And all the third one, all the decision variables are non-negative. Okay. What about the second item? All the constraints are of the equality type. Okay. You know, sometimes we have a inequality constraint. How can we deal with it? If we have a constraint in the form of lesser than or equal to, okay? Lesser than or equal, okay? It can be converted to equality form by adding new positive variable. Okay, for example, if we have, for example, look at this constraint. We have 3x1 plus 4x2 lesser than or equal 12. If we add new variables, for example, it's we add s1, and s1 is positive, we can render this lesser than or equal to equal. Okay, because this, the left hand side is always lesser than or equal, right? The right hand side. So you add positive number to the left hand side, then you can make it equal, right? You add new variable, okay? Now positive variable, okay? You add one more variable in order to render the lesser than or equal constraint to equality constraint. Yes. 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 We that one is it's the third condition. All these variables are non-negative, right? You add new variable. All this variable must be non-negative. Don't worry, it's not COVID. It's not flu A or flu B. But this is annoying. Okay, so the fourth one, a constraint in the form of greater than or equal to, okay, can be converted into equality form by subtracting a non-negative slack variable. Okay, this the idea is what it's similar to what we did to the less than or equal to. If you have left hand side which is greater than the right hand side, you see that if we subtract it, the left hand side by a positive number, it can be equal, right? Okay, so we add new variable. Okay, we call it slack variable. Okay, but this time we subtract it. Okay, so you see that any linear programming, we can convert it to standard form. Okay, we can write it in a standard form. So for the standard form, it must be written as a minimization, right? Yeah, minimization, and all the decent variable must be non-negative, and all constraints must be in a equality type. not inequality, equality, okay? Okay, so now we consider the objective function alone without constraint. The question is, how can we solve the linear programming? We can do it by analyze the objective function. And if we look at the objective function, for example, we maximize Z. Z is a summation of Cj xj, okay? C1 x1 plus C2 x2 plus C3 x3, and so on, okay? From x1 to xn. And we sum up everything, okay? And you see that if we fix the Z, okay? The value of the objective function to be constant, we have a set of x1 to xn, right? An infinity set of that. We have infinity point of that. That satisfy this equation, right? Okay. For example, if we choose z to 0, okay, z 0, and we have number of points that satisfy this equation, we call it isoprofit front, okay? A front or a set that have equal objective function, okay? Then we call isoprofit. Okay. Or we can treat it as a hyperplane, okay? It's a hyperplane. If it's 3-dimension, it's a plane, right? But in higher dimension, of course, it's hyperplane because you cannot write it as a normal plane, okay? But in 3-dimension, for example, it's a hyperplane, okay? In certain plane, all the points belong to that plane has the same objective function, okay? If you change a plane, okay, for example, here, it's a 2-dimension. If we change the plane from this yellow line to this teal line, okay, you change the objective function. But all the points in the same line, x1, x2, in the yellow line, has the same value of the objective function, right? That's the reason we call it isoprofit, okay? And we can draw this vector, the bright green arrow here, show the vector of the gradient, or the vector of, what is it? The gradient of the objective function. If we go this way, you see that the objective function change. And this gradient is perpendicular to, is orthonormal, right? Perpendicular to the hyperplane. Okay? So if you want a point or a solution that has a maximum value of the objective function, you should go this way. You should follow this direction, okay? This gradient direction, okay? If you want to minimize it, you go opposite way. You have to go down this way. All right? So for any objective function, because it's a linear function, right? You must write the gradient. You must define the gradient of the objective function first. And then the gradient define where to go, right? A minimum or maximum, you follow the gradient. Okay? You go the same direction with the gradient, you maximize it. You go backward in the opposite direction to the gradient. Of course, this is minimum. Okay, so now consider the following objective function. For example, if we want to maximize x1 plus 2x1, 2x2, okay, x1 plus 2x2, this way. The simplest way to find the maximum point is you draw the gradient of this function, x1 plus 2x2. Come on, it's two dimension. It's very easy to find the gradient. Gradient for this one is this direction. Okay? If you don't know how to find the gradient, it's very simple. Well, take the coefficient in front of x1 and x2, okay? It's 1 and 2, right? You draw a line from origin to 1, 2, okay? The line that pass origin and 1, 2, it's the gradient of this objective function. That means, well, if we follow this way, okay? If we follow this way, we maximize this function. Okay, the next one, maximize minus 3x1 plus x2. Okay, we draw a line from 0, 0 to minus 3, 1, right? This point. Okay, you got this. Okay, this is the gradient. Okay, this direction is the gradient. You maximize it, you follow this way, this direction. How about this one? Minus 3x1 minus 2x2. We follow this gradient, okay? 0, 0 to minus 3 minus 2. And the last one, yes, 0, 0 to 1 minus 1, okay? This line. Okay, any questions? Any questions? I mean, hmm? Yes, it's linear, linear. Draw area line. What we draw here is not objective function. It's a gradient of the objective function. Okay, and why is that so many lines? Because we considered 4 objective function, right? If we consider only the first objective function, of course, you consider only the blue line here. Okay. The isoprofit line or the objective function must be perpendicular to this gradient. Okay, is orthonormal of the isoprofit. Okay, so by consider the objective function only, it tells us the direction to go, okay, but not the solution. Because you see that if you want to maximize the first function, okay, consider the first function x1 plus 2x2 this way. You can go to infinity in order to maximize it. Okay, so you get no solution at all. It's just tell you the trend where to go, which direction you should go. Okay, so we need constraint because the constraint define the feasible region. If you don't, in linear programming, you see that you can go to infinity, or you can go down to minus infinity, right? To the negative infinity to get a solution without constraint. Okay, so let's say if we have constraint like this, we have three constraints, inequality constraint. The first constraint define this area. Okay, this part can go up this way. Okay, any on the right hand side of this line. Okay, or and also we have this inequality constraint also, the left hand side of this dashed line. Okay, and the third constraint we consider above this dashed line. Okay, so these three constraints form this triangle. Okay, this triangle, and this triangle, all the points in this triangle satisfy both 1, 2, 3 constraint. Okay, so the point, the set of points that satisfy all the constraints, we call it feasible region. Okay, here is our feasible region, this triangle. Okay, okay, now we have feasible region. We define the feasible region. Okay, these three inequality constraints define the feasible region already. The question is, if we want to maximize the one objective function which has this gradient, where is the maximum point? Where is the maximum point? This is our constraint, right? Oh no, gradient, right? Gradient of our objective function. We want to maximize it, we go this way, right? Okay, you should go this way, but we must remain inside the feasible region. Okay, and remember that the line which is perpendicular to the gradient, we call it isoprofit, right? All the points in this front has the same value of objective function. Okay, so we should go further along this line, along this gradient. Okay, until we reach the last point, which is remain inside the feasible region. Okay, here is the solution, this point. Okay, so this point is our solution. Okay. And only this point because all these points in the same front, the same isoprofit, had the same value of objective function. However, these points are not feasible, right? Only one point here is feasible. Okay. Only one point here is feasible region, is inside feasible region. And why this is not the solution, this point? Because here has smaller objective function, right, compared to here. Okay. Now, what is the minimum point? Which point is the minimum point? Minimum point should be here, right? Okay. Okay, so now consider the following linear programming problem. You can solve this problem by graphical method. You can do it by using the GeoGebra. Yes. Can you do it by yourself? Not you don't need 3D. Just yes, just a graphic. GeoGebra calculator. Okay. Okay, this one. See, geogebra.org calculator. Then you add each constraint, okay, and define the feasible region first. Okay. After that, you draw the gradient of the objective function. overlap อืม okay so this is a feasible region. I believe that some of you may, well, have already defined it. Okay, from A to B to C to D, E, F. Okay, just that. Okay, so the next one is you draw a gradient of the objective function. The gradient of the objective function is here, the orange arrow here. Okay, coming from this here. So where is the maximum point? Where is the maximum point? Yeah, see. Okay. This is the maximum point. Okay. No, it's not that it's not that meaning. We have to draw a perpendicular line to this gradient. Yes, and we try to find the perpendicular line, isoprofit, which is far most. Okay. What about minimum? Minimum point, where is the minimum point? Hmm? Yes, it should be F. It should be F here. Okay. Yes, you can try if you know all the coordinate, and you can try. You can do that, but you have to test at every point. Mhm. ไม่ใช่สั้นที่สุดเอาเป็นภาษาไทยนะอันเนี้ยมันบอก gradient โอเคไหมแต่ gradient เนี่ยจะตั้งฉากกันกับ isoprofit เพราะงั้นเราก็ต้องลากเส้น isoprofit นะไปให้ไกลที่สุดเพราะถ้าไปไกลที่สุดก็คือ objective function มากสุดไปได้ไกลที่สุดถามว่าตรงนี้ยังลากได้ไหมไม่ได้แล้วเพราะมันไม่มีส่วนใดส่วนหนึ่งที่มันตัด feasible region แล้วใช่ตรงนี้คือไกลที่สุดที่มันยังตัด feasible region อยู่โอเคมินิมัมพอยต์ก็เหมือนกันทำแบบเดียวกันแต่ไปให้ลงมาต่ำที่สุดอืมเอเป็นไปไม่ได้เลยเห็นผลว่าเนี่ย A if we consider A maybe perpendicular line is here right okay you see that we can go further down right yeah until we reach here perpendicular to it but one thing you well must be careful that the scale if you want to draw a perpendicular line the scale must be the same this one the scale is not the same okay but more or less yes you must use a symmetric scale okay symmetrical scale but it's okay this just give you the concept because I know that no one look at this point and read the point if you want to know the what's it the coordinate here the point here what should you do for example the C for example is C you know that C is defined by this intersection of this constraint no the constraint number 2 and constraint number T right so you should find this intersection of this constraint okay in order to don't read it exactly from the graphic Okay. So let me conclude. The technique we solve the linear programming for a very simple one using graphical solution. The first one, you graph all constraints and determine the feasible set first. Okay, graph all the constraints and define the feasible region. Then graph the gradient of the objective function. Okay, you draw gradient of the objective function. The third one, shift the contour line into the direction of gradient of the objective function until the last feasible point is reached. Okay. Then, for example, this point, you find the intersection of the constraint involved in that corner. Okay. Okay, now we consider 4 special cases. If the constraints do not define a certain region, feasible region, we call it no feasible solution. Okay. You don't have to consider the gradient of the objective function, anything, because you don't have feasible region. We don't have feasible region, of course, no feasible solution exists. Okay. The next one, if the constraint form the feasible region, however, it's not the closed set. This one is open set, right? It's not closed set. If the solution is not this direction, the solution, I mean the gradient is, well, leading to this way. You see that we don't have solution, right? Because infinity, right? If we go to infinity, of course, the objective function reach infinity, which is the maximum. That means, well, in this case, is we have an unbounded optimum solution. That means the solution is not defined. Okay, we cannot say the solution because it's unbounded. Okay. Okay. We call it unbounded optimal solution. Okay. The next one is dual degeneracy. The next one, dual degeneracy, is when one of your constraints is parallel to the objective function. Okay. What happens if your objective function is parallel to the constraint, one of the constraints? The solution is not at the corner anymore. Okay. Remember that this direction is the gradient, right? So what is perpendicular to this one is a objective function, right? And the objective function, if the objective function is parallel to this constraint, what happened? All points here have the same objective function. So in this case, the solution is not one single point. You have multiple points that has the same objective function. Okay, we call it dual degeneracy. This case. Okay. In this case, the solution is not at the corner anymore. Okay. The next one is primal degeneracy. For primal degeneracy, it's yeah, I explained from this graphic. Normally, our solution is at the corner, right? At the intersection of the constraint. We call it corner like this, okay? Except in the case of dual degeneracy, where the solution is not at the corner, but all point at that faces, right? Now, imagine that the solution is still at the corner. However, normally, how to define the corner? The corner at the intersection of constraint, okay? If you have two dimension, I mean, two decision variables, you need at least two constraints, right? In order to define one corner, okay? Consider this case. If our solution is here, however, we have three constraints define this corner. So you see that this corner is excessively defined because it's defined by number of constraints more than we need, right? It's excessive, right? But the point is, if you believe that, okay, this is our solution, and this solution is defined by this constraint and this constraint, okay? And you, well, maybe you tell your boss that, wow, our objective function is defined by this constraint. Let us invest on new machine in order to move this constraint out. What happened? If you shift this constraint to the right hand side, do you think the objective function change or the optimum solution change? Hmm? What do you think? This corner defined by constraint 1, 2, 3, right? You invest on, well, new machine, and you can shift constraint 2. Maybe constraint 1, okay, constraint 1 to the right hand side. Do you think that your solution, you will get more value of the objective function? You will get higher objective function? Constraint number 1 to the right hand side. Yeah, the answer is no, because this point defined by 3 constraints. You move one constraint to the right, but the solution doesn't move because it's already defined by other 2. Okay, this case we call primal degeneracy. Okay. Okay, so now we learn how to solve the linear programming using graphical method. Okay, the graphical method is quite intuitive, right? And but the main limitation of the graphical method is what? What is the main limitation of using graphical method? Right. If you have 3 decision variable, no, impossible to draw it, right? Or you have 4, 5, 6 decision variable, you cannot draw it anymore. So from the idea of graphical method, we're going to develop a algebraic solution technique. Okay. For algebraic solution technique, we start from the canonical form of the linear programming. For canonical form, we write, this way. Minimize or maximize of something. And for the constraint, you must write as a lesser than or equal, okay? But of course, later we will transform this one to equality constraint, okay? But this is a canonical form. It can be minimized or maximized, it's okay. But everything you write as a lesser than or equal, okay? But the most simple case, the right-hand side must be positive only. Yeah, in short, B must be positive, okay? B must be positive. And no equality constraint exists. You may have question, or what to do if I have equality constraint at the beginning? We will do it later, okay? We deal special case. The case where we can write a canonical form, okay? Lesser than or equal. And the right-hand side is positive only, okay? And all decision variable must be non-negative, okay? Like this. X must be greater than or equal 0. Okay, from canonical form, you change everything to canonical form first. If you have an unrestricted decision variable, you change it to non-negative decision variable and lesser than or equal, okay? Then each inequality constraint, you add slack variable to that inequalities, okay? And once you add slack variable, it renders the inequality constraint to equality constraint, right? Okay. You have one inequality constraint, you add one slack variables. You have two inequality constraint, you add two slack variable. Okay. This way. So we can write from canonical form here. We can write this form. Okay. Or we can write it as a matrix because you add select variable. Okay. So what is I here? I is identity matrix. Yes. Because it at the identity as a it's 1, it's 2, it's 3, right? Okay. And the algorithm we're going to use, we call it simplex method. Simplex means simple. This is the simplest one. First, remember that all these variables must be non-negative. Okay. Otherwise, change the variables. Okay. For equality constraint, you cannot do it now. Use two algorithm. Okay. I'm going to tell you later. And all constraint must be in the form of this canonical form, where the constant is positive, okay, and you have lesser than or equal, okay. If you cannot write this form, use two-phase algorithm. You cannot do it now, okay. Just use two-phase algorithm. I'm going to tell you later. And once you write canonical form, you add select variable, right, to make it equality constraint, okay. And put all the variables and coefficient in this table. Okay, we have table here. Okay, you know that we have A, which is m by n, right? And we have identity metric here, which is m variable, right? Equal to S, right? So in this matrix, we have n plus m variables. And we have m relation. We have m equalities, right? Equations. So degree of freedom is, well, n plus m minus m, right? So degree of freedom is n. What does it mean? It means if you want to solve this system, you have to define at least m variables. Okay? So we select m variables as basic variables. Okay? And the rest, we call it non-basic variables. Okay? For non-basic variable, well, totally we have n non-basic variables, right? So each time we solve this problem, we have to set non-basic variable to be 0. And we solve for basic variables. Okay. Yeah, you can, later you can read the algorithm, but I'm going to explain the algorithm by example. I think it's easier to understand from the example. Let's say we have this objective function. We want to maximize 40x1 plus 50x2 plus 100. Okay. We write this objective function as minimum. Okay. We minimize minus 40 x1 minus 50 x2 minus 100. Okay. And each, oh, I skipped this. Okay. All right. From the first one, we have this canonical form, right? The first inequality constraint is 2x1 plus x2. We add s1. Okay. Equal 12, right? So 2, oh, sorry, 2, 1, 1. This is a coefficient, right? 2x1, 1x2, right? Plus s1, it's 0, 12, okay? 0, s2, 0, s3 becomes 12. And from the second, minus 4, right? 5, 0, 1, 0, 20. The next one, 1, 3, 0, 0, 1, 15. Okay? And everything look perfect because on the right hand side, we have positive number, right? Okay. So the last line is the coefficient of the objective function, minus 40, minus 50, 100 here. We move to the right. So minus 100 becomes 100. Okay. So the point we start, remember that we have 5 variables, right? 5 variable, but we have 3 conditions. So we need 3 basic variables and 2 non-basic variables, right? So at the first round, at the beginning, we set x1, x2 to be our non-basic variable. We set s1, s2, s3 as our basic variable. Why? Because you see that if we set x1 is 0, x2 is 0, because they are both non-basic variable, right? So we set them to be 0. If x1, x2 are 0, we know that s1 must be 12. All right? Also, this one is 0, this one is 0. Then s2 must be 12, 20. Okay? 0, 0. So this one must be 15. Okay? So at the beginning, we know the solution, right? We call it basic feasible solution. It's not the optimal solution. It's just basic feasible solution. Okay? And the first point is 0, 0, 12, 20, 15. Okay? This is the first point. You can think about, okay, now we are at the origin because we have only 2 variables, right? 2 distant variable, I mean original one, x1 and x2. And they are both 0, so it's at the origin. And what about 12, 20, 15? These are the value of the slack variable. Or the physical meaning of it, the slack variable means how far from the constraint. How far is that point from the constraint? Right? Because on the left-hand side, the original one is lesser than or equal. And you add slack variable to make it active. And you need 12, all right? So you still have 12 units until you reach that constraint. Okay? This one also, you add S2, right? And S2 now at 20. At that point, in order to turn this inequality constraint to active constraint, to equality constraint, you need 20 unit. And it also apply here, right? Select it's 15. You need 15 units in order to turn this one, the inequality constraint, to be active. Okay. And this is what really happened in graphic, I mean. Yeah, we are at this point, 0, 0. Okay? And 12, 20, 15, it's slack variable. How far we are away from the each constraint. Okay? Okay. Now we look at the bottom line. Bottom row. Now x1, x2 is non-basic variable where we force them to be 0, right? But you see that if we allow them to increase by 1 unit, what will happen to objective function? If x1 increase by 1 unit, changing from 0 to 1, what will happen? what will happen to objective function? The objective function will be reduced by 40. Right? Because now it's 0, so it becomes 0, right? But 1 is changed from 0 to 1. It will go down by 40. What about x2? Yeah, the objective function will be decreased by 50. Are we going to minimize it? Can you tell me what to do in order to improve the objective function? We should increase x2, right? Because if we increase x2, we can lower the objective function. Okay? What about x1? x1 is also right, but 1 unit of x1 reduce 40. 1 unit of x2 reduce 50. So we choose x2, right, to increase. We allow x2 to increase. Okay? So you look for the coefficient, which is the most negative one. You look at this column, x2. Okay? In the next round, we will add x2 to our basic variable. Now it is non-basic variable, but in the next round, it will be our basic variable. Okay? But if we want to include x2 as our basic variable, we have to remove the original non-basic variable out, basic variable out, right? Because non-basic variable is 2, right? And basic variable is 3. If you add one more, add x2 to be basic variable, you have to remove something out. Okay? So what to do? Find the b over a. This b divided by a. A in this column. B by a. B divided by a. Okay? And b by a, the ratio of b and a, the fraction of b and a must be positive, but smallest. Okay? We choose the smallest one. Okay? Why we choose that smallest one? Because you know, on the right hand side, it's a slack variable, right? How far we are away from the constraint. Okay? So we divided b by a. We try to find which slack variable is sensitive to the increasing of x2. Okay? So here, well, it's 12 by 1 is 12, right? 20 by 5 is 4. This is 5, right? So we choose this one. In the next round, we insert x2 to the basic variable and remove s2 from basic variable. Okay? The next round, s2 becomes non-basic variable, and x2 becomes basic variable. Okay? So once we choose this point, okay, we have to do something with our table. We must make this position to be 1, and other place in the same column must be 0, like this one, you see. all the basic variable. In the first round, we have basic variable where for S1 is 1, right? The other place 0, 0, 0. S2 is 1, other place 0, 0. Okay? So in order to make this position to be 1, we have to divide out by 5. Okay? And you do some calculation. Yes. Make it 0 here. Okay. First, we divide it by 5 first. We got this table. Okay. And from this table, the next task is make this one to be 0 and make this one to be 0. Also this one to be 0. How to make that this one to be 0? How to do it? You subtract every place, right? By this line. Subtract this line by this line. Okay. 2 minus 4 by 5. 1 minus 1, right? And then next one, 1 minus 0. 0 minus 1 over 5. 0 minus 0. 12 minus 4. Okay. What about this line? This row. How to make this line, this row to be 0? We times, we multiply 3 to this line first, and then subtract with this line. Okay. And for the last line, the objective function, you multiply 50 to this one and subtract this. Okay. So it's rendered to this. Okay. You see the second column. Now it's 0, 1, 0, 0. Okay. Also pay attention to the very first column. In the very first column, I replace S2 with X2 already. Yeah. To remind ourselves that X2 is our basic variable in this round. Okay. Okay. You can do it by using Excel. Or in my course view, I think I upload the Python file for a code for simplex method. You can play with it. Mm-hmm. Okay. Okay, we reached this table already, right? Now we look at the coefficient again. The coefficient. We know that. Oh, just one moment. The connection is unstable. It should be okay now. Okay. Do you think that we reached the minimum point yet? Hmm? No, not yet, because the coefficient of x1 this time it's negative 80, right? We still have negative coefficient of the objective function. That means if we increase x1, we can further reduce the objective function down. Okay. So the next round, x1 will be our basic variable. And we have to get rid of one of the original basic variables, okay? We use b over a again. Test the b over a. So this one has the smallest positive b over a, okay? Okay, this one. You don't have to consider this one because this is negative. Okay, we consider only positive b over a. The smallest positive. Okay, so this is the target. In the next round, x1 will be our basic variable, and we're going to remove s3 from our basic variable. Okay, we have to multiply by 5 over 17 to make it 1. Okay, multiply all of this. Yes. Okay. Then you have to make this column to be 0, except this one, except this position. Okay. Then you got this 0, 0, 1, 0. Okay. And on the most left, you see our basic variable. Our basic variable is now x1, x2, x1. Okay. I skip one point, you see. From the very first step, we start from 0, 0, right? And the second round, we move from 0, 0 to 0, 4, which is this point. Okay. And once we move through this one, we move to this point. Okay, you see this, right? This point. Okay. We are at the third round. Not finished yet, because we still have negative coefficient here. So you see that if we allow S2 to increase, we can further reduce the objective function. Okay, so S2 will be our basic variable in the next round. And we have to remove one. And that one is S1. We're going to remove S1 from our basic variable, and S2 will be our new basic variables. Okay, we use the same testing. Okay, we make this position to be 1, and then we try to make this one to be 0, 0, 0. Okay, this is the point where our basic variables consist of S2, X2, and X1. Okay, so you see X1 is 21 over 5. X2 is 18 over 5. S1 is 0. S2 is 94 over 5. S3 is 0. S1 and S3 is non-basic variables. Of course, they must be 0. Okay. The point actually here. Okay, you see that by using simplex method, we travel through the corner, right? Each corner. We relax some non-basic variable, right? We treat non-basic variables to be 0. Okay, that means we relax it and we roaming through each corner. Okay. Okay. So now next example, we maximize x1 to x2 plus x3. Okay, and we have these constraints. Though this one is greater or equal, however, once we treat it in order to make the right hand side to be positive, then this one becomes lesser or equal. Okay, it's canonical form now. Yeah. Okay, so from this one, we write a table. Okay. From the first one, 2, 1, minus 1, 1, right? 2 minus 2, 1 minus 1, 1. 0, 0, 2. Okay. And the second constraint, 2 minus 1, 5. 2 minus 1, 5. 0, 1, 0, 6. Okay. The next one, 4, 1, 1. 4, 1, 1, 0, 0, 1, right? And on the right hand side is 6. Okay. And what about the constraint? Constraint is minus 1, minus 2, and minus 1. Minus 1, minus 2, minus 1. Okay. 0, 0, 0. 0. Okay. So at first, at initial, our basic variable weights, our basic variable include S1, S2, S3, right? X1, X2, X3 are non-basic variable. Okay, that means they are 0, 0, 0. Okay, so we are at 0, 0, 0, 2, 6, 6. Okay, and we should consider x2 to be our basic variable because this is the most negative coefficient. Okay, and we perform ratio of b and b over a. Okay, testing. Okay, this one is 2, right? This one is 6. We skip this one because this is negative. Okay, so S1 will be removed from the basic variable in the first round. In the next round, we will have S1, X2, S3, right, as basic variable, and the rest are non-basic variables. Okay. Now the next round. This is the negative again. We're going to include X3 as basic variables. And we remove S2. นะครับตามวิดีโอแล้วกันครับ Okay. So what do we have now? We have basic variable x2, x3, s3, right? And you see that no more negative coefficient. Then we stop here. Okay, we stop at this point. This is our solution. This one, this one, this one, this. Yes. The smallest positive of B over A. This one, you skip x2, right? Because this is negative. This one is S by 4, which is 2, right? And 4 by 2, which is 2. You can take any one. S2 or S3 is already. Anyone. Mm-hmm. Okay. Any questions? You have questions? Hmm? Huh?
I do not good right now, so I can
Mm-hmm.
like have a permission to go for the center.
Yeah, you can go. Okay, no problem. Any questions? Okay. I'm recording the video. It's all right. Then later you can watch it. Mhm. Okay, you see that's very simple as long as the original problem is in the correct form. Where you can write a canonical form, everything is fine, right? Now we consider the case, a special case. This problem, minus 3x1 minus 2x2, okay? And we have two inequality constraints, which seem to be okay, right? On the right-hand side, they are both positive, and they are in canonical form. All right, so we just create a table. S1, S2, just that. It's very simple. Basic variable in the first round are S1 and S2, all right? Okay, so you see that this is a negative, right? This one also negative, but this one is more negative. So we choose this one, right? The most negative one. And the ratio here is 1. Ratio here is 2. So yeah, we go this one. Okay. Then the second round, we obtain this table. Minus 1, 1, minus 5. Okay, you have minus 5 here. It's okay. This one is negative. No problem. We still have this one, which is positive. S2 will be non-basic variable in the next round. So we move to this point. Yeah, we got this table. The problem is, the third round, we got this table. This table indicates that we can further decrease the objective function, right? Because this is negative. Okay. But the problem is we cannot remove x1 or x2 from the basic variable. We cannot remove anything from the basic variable, right? Because they are both negative. Okay, so all coefficients are negative. We stop here. We cannot go further. And this, once you arrive at this similar condition, similar table like this problem is unbounded optimum solution. Okay. This is unbounded optimal solution. And you see that it's unbounded because, of course, you can go this way to reduce the objective function, but you cannot further. The solution is not defined. Okay, let us break for 10 minutes. Okay. We will come back with the, the two-phase algorithm. What we learn is just the basic algorithm when everything is defined. Okay.หลังสอบเสร็จได้อะไรนะ จะเตรียมแอคชั่นไปวิดีโอหรืออะไรอย่างนี้เพราะจริงๆแล้วในเราเทอร์โมที่ตั้งใจไว้ครับอยากให้ทำเวิร์กช็อปแข่งเวิร์กช็อปก็จะเป็นอะไรนะจะมีประมาณ2-3 สัปดาห์ที่จะให้จะแจก Data แต่ Data ก็เป็น Data ในเซฟเวอร์แล้วก็ให้ไปทำโมเดลทดสอบ Data แล้วก็สร้างในแอคทิวิตี้เป็นโมเดลเองอะไรอย่างเงี้ยทำให้ง่ายอยู่ในนั้น
เพราะว่ามันตอบก็ทำไม
ครับกำลังคิดอยู่เหมือนกันว่ามันเลยมาพอสมควรตอนเริ่มครั้งแรกเริ่มคนหนึ่งเลยนะเริ่มสัปดาห์หนึ่งอาจารย์เขาเริ่มสอนตั้งแต่สัปดาห์แรกเลยนะโอ้ยจริงๆแล้วการเข้ามาสอนเมื่อก่อนเข้าใจนะผ่านขั้นมาช้าเราเริ่มสัปดาห์แรกๆทำเนี่ยเราก็ไปรีรันกันอืมก็ประมาณนั้นเดี๋ยวลองดูอ่านเพราะฉะนั้นเป็นไปเรื่อยๆอาจารย์เข้าใจก็มาถามเหมือนกันว่าเล่นได้ไหมเพราะไม่งั้นเนี่ยจะตอบสัปดาห์นี้ว่าเราก็มีปัญหากันอยู่สัปดาห์ที่แล้วแล้วไปเรียกสัปดาห์ที่แล้วอ๋อแกบอกตอบสัปดาห์ที่แล้วสายงานก็ไม่ทันอีกเมื่อไหร่จะแก้ปัญหาถึงทันครับไม่คือปีแรกทำอะไรไหมเพราะเวลาทำจดหมายได้ช้าก็ไม่ยอมทำแยกกันระหว่างการได้ทุนกับการรับเข้าจริงๆรู้รับเข้าแต่ไม่ทำให้รอให้เรื่องได้ทุนประกาศเรื่องได้ทุนประกาศ2 สัปดาห์เปิดเรื่องอะไรอย่างเงี้ยสวัสดีครับยุ่งอยู่เหรออ๋อโอเคว่า ได้ส่งชื่อมาได้ไหมช่วยเขียนชื่อส่งให้หน่อย30 นาทีก็ได้โอเคขอบคุณครับขอบคุณครับไป3 รอบเอ็กซ์ Okay, so let us continue. You learn about simplex method, right? You know the concept. What still remain? The first one is we need a what's it? A problem which is in the defined structure, right? The problem must be in a canonical form, and the right hand side must be positive always of the inequality constraint, of course. What else? The algorithm cannot handle equality constraint, right? What we learn now is just, whoa, okay, we start from canonical form, not equality constraint, right? So we have to deal with it. And the other one is the initial point must be feasible first. If your first initial feasible solution, if your initial solution is not feasible, then forget about it. The simplex method cannot do it. All right. So then, in order to what's it, to handle on this thing, I mean equality constraint, and also when you have a greater or equal inequality constraint, okay, you need two-phase algorithm. Okay. So when you when you solve the linear programming using simplex method, you just check it first if you can write them in the canonical form or not. Okay. And if your problem contains equality constraint or not. First. For two-phase algorithm, if your problem contains equality constraint, you have to handle it this way. First, from equality constraint, x1 plus x2 plus x3 equal 2, you add E1 to this problem. E1, right? You see that? That doesn't make any sense, right? You add E1, okay. X1 plus x2, x3 plus x3 must be 2. And you add another one, E1, and make it, force it to be still 2. What does it mean? E1 must be 0, right? Okay, so that is the aim of the first phase of the algorithm. Okay, but you have to handle this way in order to find the feasible solution first. And the next one, if you have greater than or equal, you see that on the left hand, on the right hand side is it might be positive. You cannot make it positive without using greater than or equal, right? If you change it to lesser than or equal, it must be -2, which is negative already, right? So you make it positive, right hand side positive, and allow the greater or equal, okay? And we have to transform it this way. x1 plus x2 plus x3 minus s1 plus e1. Okay, you subtract by slack variable, and you will have to add e1. We call e as the auxiliary variables. Okay. If you have two equality constraint, of course you need E1, E2. Yeah. If you have two greater than or equal equality constraint, of course you need more E1, E2. It's all right. So the name of two-phase algorithm is we have two phase. The first phase is we sum up all E1 plus E2 plus E3. Any auxiliary variables we introduce, okay? We sum them to W, okay? And the first phase of the algorithm, we going to find the solution where the W is 0, right? Because in order to satisfy all these equations, E summation of all auxiliary variables must be 0. Okay. All right. So now the example. We minimize this objective function and we have two equality constraints. Two equality constraints. Yeah. Okay. So we add E1 here, right? And we add E2 here. Right? E1, E2. Okay, so the first one, f, this is our objective function, f, okay? Then we just rearrange it because f equal to x1 plus, we change it into one side, okay? And because w is summation of E1 and E2, right? E1 plus E2, it's w. So we can write this way, E1 plus E2 minus w is 0. Okay? And you can combine all the first equation, the second equation, and the last equation, right? And you can eliminate E1, E2 this way. Okay, right? Very simple. It's this one. It's E1. You subtract this one by this one and this one. Okay. And E1 will cancel it out. E2 will cancel it out. Okay, you got this. Okay, now we are ready for the phase 1. We write this table. From this table, you see, we write the coefficient of from the first constraint. 3 minus 3, 4, 2 minus 1, 1, 0, 0. Okay, right? This from this one. And the second row from the second constraint. 1, 1, 1, 3, 1, 0, 1, 2. Okay, and this line from objective function. This line from this one. -4 to -5, -5, yes, yes. Okay, and remember that for the phase 1, we consider only W. Our aim is to reduce W to be 0, force W to be 0. Okay. So we can choose between this column or this column. Is all right. They have the same -5, right? Coefficient. Let's say let's choose this column. Okay. We introduce x4 as our basic variables. And while E1 will be released. Okay, we replace the basic variable. We replace E1 with x4. Okay. And from here, this column is more negative than this column, right? So x2 will be enter the basic variable set. And E2 will be removed. Okay. Then we obtain this table. And from this table, congratulations, our W is 0, right? W already 0. Okay. That means, well, we can move to the second phase. Okay. And we don't care about E1, E2 anymore. We can remove this row, remove this column, remove this column. Okay. Now our table is reduced in this form to this form. Okay. So from this table, we continue with the simplex method, the phase 2. We introduce x5 as our new basic variables, and we remove x2 from the set of the basic variables. Okay. Okay, we obtain this table. Then it's finished because no more negative coefficient. Okay. The next example, we have maximization of this function, x1 minus 2x2 plus x3 lesser than or equal 8. 3x1 minus 2x2 is greater than or equal minus 18. Okay. This one also 2x1 plus x2 minus 2x3 lesser than or equal minus 4. Which equality, which constraint is the problem? Which constraint is the problem? No, the third one. This one you multiply by negative. This one turns to lesser than or equal, and you got positive on the right hand side, which is perfect, right? But this one, you have negative here. In order to make it positive, it's turned to, yeah, greater than or equal, right? So you have to transform to this. For the first two inequalities, we add S1 select variable, S2 select variable. But for the third one, you subtract by select variables and you add auxiliary variables. Okay, in order to handle greater than or equal. And W in this case is W is E1, right? We have only one variable contribute to W. So E1 minus W is 0. So this one subtract by this constraint, you obtain this one. Okay. The last line. Write all these things in Tableau. In the table. Okay. So you see that our our objective, the aim of the first our aim of the first phase is to what? To make W to be 0. Okay, drive W to be 0. So, okay, we focus on this column because it is negative, right? And yeah, this is 8, right? This is infinity. This is 2. So this is smallest B over A. Okay, do this way. Okay. Luckily, W is 0. So we can remove this column. We remove this column and we can enter the second phase, the phase 2. Okay. But if you cannot make W 0, that means the problem is infeasible. You cannot enter the second phase. Okay. Okay. From this one, this is the most negative, this column. Okay. And we have only one variable, which has a positive coefficient. Okay, we make this, okay? And this also, this is the most negative. However, we cannot use this column because all the coefficients are negative, right? Only this available, yes. We do again, this is the remaining negative coefficient, x2. Yes, this, we do it again. Okay, we arrive at this table. This table is negative, but all of them, all of the coefficients are negative. What does it mean? This is unbounded optimum solution, right? Unbounded optimum solution. Okay. Now we minimize this objective function. Now we have x and y. It's all right. X and y and x1, x2, it's all right. The same. For the first constraint, it's okay. Just add select variable. This one also add select variable. But this one, you subtract by select variable and you add E1, right? This one, you subtract by select variable and you add E2. Okay. What about W? W is summation of E1 and E2, right? So E1 plus E2 subtract by W becomes 0. You, from this equation, you subtract by this one and this one, okay? You obtain this, all right. Okay, you write everything in the table. Okay, we got this table. Okay, our basic variables for in the first phase is S1, S2, and E1, E2, right? Look at the most negative one here. Okay, then we drive W down, okay, to 0. The next step is this column, because this is the most negative one. Okay, then we got this W is 0. Okay, then we remove E1, E2, and also W from our table. This one, we obtain this table, then we enter the second phase. However, we cannot do anything, it just stop. Because this is the optimal solution already, okay? Because we don't have negative coefficient. Okay, any questions? You have any questions? Of course, you need practice on this thing, right? เดียวเองอะอาจารย์มีนี่เดี๋ยวนะ what do we have? Just one moment. Simplex algorithm. They, well, I think I prepare, what is it called? It's a Jupyter notebook, right? I wrote a Jupyter notebook on the simplex method two-phase algorithm. I think I upload all this file to my course view already. Yeah, a week ago, right? Maybe, yeah. So if you know how to run Python, it's okay. You can test it. It's very simple. You can run it in using Anaconda or anything. You know Jupyter Notebook, right? For Jupyter Notebook, of course, there are two different block. Here, it's a kind of comment or text, just that. You cannot run it on this thing. You can run this, right? So all you have to do is just run all this, right? Run on this. And here are explanation of what we're going to do. Yes. The coefficient from the above, right? If I did anything wrong, of course, just tell me. Okay, I will fix it. Yeah. This array of B and array of A, you see? Slack variable, surpass, and ถ้ามี Excel ก็ใช้ Excel ได้ ไม่หรอกเดี๋ยวใช้เครื่องคิดเลขอะกดทำโจทย์แบบทำแบบอะไรนะ ปัญหาหนอนแทะปัญหาหนอนแทะคือ เหมือนมีเฉลยอยู่แล้วอาจารย์ลบทิ้งแล้วก็ให้เติม ก็เป็นไปได้เป็น table มาแล้วก็ลบบางอย่างออกก็คิดเติมให้ครบ เมื่อก่อนไม่เคยให้ทำแบบนั้น เมื่อก่อนก็คือมีโจทย์ให้แล้วให้ทำทั้งหมดเลย ประมาณ20 ตุลานี่มันตั้งแต่ต้นเลยนะ ตั้งแต่ formulate ปัญหา optimization ตั้งแต่ต้นเลยอะแต่จะแยกกัน เพราะฉะนั้นถ้าทำตรงนั้นได้ตรงนี้ไม่ได้ก็ยังโอเคอะไรอย่างเงี้ย อือฮึยังได้บ้าง แต่ถ้าไปอะไรนะให้ formulate มาแล้วให้แก้นี้ด้วยเนี่ยมันจะเป็นปัญหาเพราะถ้ามัน formulate ไม่ได้พวกมันจะแก้ตรงนี้ไม่ได้ต่อถูกไหมอืมไม่รู้เหมือนกันยังไม่รู้อืมอะไรนะ Okay, so well, you can read this notebook, okay? And you see that I also upload 2 files, duality, right? But I'm going to explain about the idea of duality next week. And the other thing is linear programming with Kurobi. Yes, this one I really love it. Remember that last time we installed Kurobi in Python, right? If you can install it and make it run. So actually you can see that I write something like PAP install Gurobi again. Well, but if you know how to install it, it's okay. You can skip that part. And for a very simple problem like this objective function with 2 variables and these 2 constraints. Okay, the code is here. Okay, model, the linear programming example, and then x1, x2 is our decent variables, right? Model set objective. Yes, and add constraint C1, C2, and then optimize. Yeah. And this part is a result from my computer, right? Just one moment. Yes, from my computer. Yes, CPU Apple M2. But normally, well, because I'm not sure about that because I run Python in 2 different ways. The first one is I run everything in my computer. And the second choice is I can run it on Colab. You know Colab, right? Google Colab, yes. And the good news is you can install Gurobi in Colab. That means you can run that in the cloud, on the cloud, right? Yes, but this one it's on my computer, on Apple M2. Okay, any questions? Anything you want to discuss? Any question from Zoom? Huh? From, yeah, last year, I teach MATLAB. We use MATLAB in the class. MATLAB and Gurobi, also Excel, other things. Of course, it's much easier than Python for setup and running the Gurobi. But MATLAB is not free, you know. Yeah. But for Python, it's more complicated, but it's okay. As long as it's free. Okay. No question from Zoom. No question. Okay. So no answer also because no question. Okay. Anything? If not, we see. Yeah, we will see again on next Monday. Yes, next Monday. ทำไมอ่ะ Why? Next Monday. Why? 14หยุดก็ไม่ได้ไป14วันที่7 next Monday 7 not 14. Yeah. For any one of you while study advanced thermodynamics, advanced thermodynamics ใครเรียนบ้าง you advanced thermodynamics. Okay. Yes. Only 2. How many people at okay good. So I have to plan many things about that because we have constraint of the time. Right. So yeah, I hope that you can catch up the course before midterm, right? You're going to take an exam very soon, midterm exam. Yes. Next Friday. No, next Friday you have exam. Should be next. Yes. Not this semester, not this week, not next week. Next week you have exam. Right. The week after that. Yeah. And this week must be very busy. University must be very busy. So if you plan to come to university, this starting from Wednesday, right? You should plan. Okay, so if no question, then do you have any sample midterm question? Yes. Yes. Which slide? Just one moment. Just this slide. The previous one. Which one? Huh? How can I know? It's 53. Which one? Two face off. This one before. Yes, this one. Show me. Yes. Where the -5, yeah, right?
Yeah.
So what is your question?
We have to make this one 1. So
One.
this.
Yes.
We have to make.
Yes.
So
Yes.
we divide everything by 2.
Yes.
But here it's -7, -3. This one is okay, but this is E2 is now -7, 11. But here it's 1, 1.
Yeah, just one moment. It is this one, right? So X4 in X4 column, this one must be 1, right? And this one will be X4, right? This one 1, 0, 0. So what is the problem?
How did the other change? Because there here E2 is like 1, 1, 1, 3, and here it's -7.
Yeah, because you see that you divide it by 1 first, okay? This row is okay for you, right? X4. This row is okay, right? Okay. Then back to this here. we have to make this to be 0, right? In order to make this 0, you multiply this row by 3 and subtract here. Okay?
For everyone, if you want to make this one, like now we want to make this one 1.
Mm.
So we have to make the other 2, or
All of them might be 0, right? Except this one. Mhm.
except it can be 1.
Okay, yeah.
Now, right.
Mhm. Yeah. And well, I will tell you the reason. Why do we have to, once we identify this x3, for example, this one, x3 will be our next basic variables. That means it will not be 0 anymore, right? If it's not 0, we have to force the coefficient to be 0 because the value is not 0. Okay? So you make this one to be 0, but the other column must be, no, this one must be 1, right? But the other, yeah, must be 0 because x3 now basic variable is not 0 anymore. So the coefficient must be 0, 0, 0. There's a reason. Okay. And why this is only this column is 1? Because you see, for other column, if it is basic variable, the coefficient is 0. Right? For example, this one we have S1 as, no, which one is basic variable? We start from this one. Okay. Yeah, here, right? We have this one as basic variable, which is not 0. So we force this one to be 0, 0, 0. Okay. I'm not sure my explanation is clear or not, but yeah. Yes. ใช่ Mhm. So you see from even, yeah. Let me show you again this. No, this. Once you see that from this, once we add slack variable, S1, S2, S3, right? And in the first round, the basic variables, our basic variables are S1, S2, S3, right? Then we force everything to be 0 because they are non-basic variable, right? Then S1 is 2, S2 is 6. Yeah, the same. And once you change your basic variable, then the same. Yeah, you do it. Okay, so for example of midterm question, yeah, I will try to show you. Wow, I will distribute some of the question from previous exam. However, it's totally different from this year. No. Previously it was too difficult. It takes too much time. Okay, so let's call the day. Okay, let's call a day.